everyone, this is Javier Melendro from Polytechnic University of Madrid, and I'm going to show you here in this quick presentation our most recent paper that consisted in the design of a gradient index lens with an integrated polarizer for dual circular polarization at W1. So, as you may know, a gradient index lens has a relative permittivity that decays from its center to its edges. This is due so the lens can compensate for the different paths of the rays in order to achieve plane wave emission. We would have the relative permittivity profile shown in the blue curve. However, in order to approach it to a practical solution, we need to approach this blue curve to a step function. This means that we designed a 5-layer lens with given relative permittivities. Now, to achieve the exact relative permittivity required for each layer, what we did in the paper was to perforate each layer, as shown in the image. So here are some results of the gradient index lens antenna. As you can see, the lens can collimate the rays into a single direction, achieving plane wave emission. Here are some cuts of the radiation pattern. As you can see, there's been an enhancement of the directivity, a notable enhancement of the directivity. Besides, if the square waveguide is displaced along the focal plane of the lens, the lens can achieve beam reconfigurability up to ± 30 degrees in the azimuth and elevation planes. Now, comprising the dielectric polarizer, here we can see how when the T10 mode is excited in the square waveguide, the vertical polarization is converted by the polarizer into right-handed circular polarization, whereas if the T01 mode is excited in the square waveguide, the horizontal polarization can be converted into left-handed circular polarization by the polarizer. The whole concept of the polarizer is based on an anisotropy in the dielectric slabs and the definition of two effective permittivities. Now, showing some results of the beam reconfigurability, as it can be seen, as the square waveguide is displaced along the focal plane of the lens, the beam can be tilted up to 30 degrees, keeping a low axial ratio below 3 dBs. Now here's a picture of the gradient index lens with the integrated polarizer that was manufactured as a single piece. A dielectric frame was also manufactured to achieve beam reconfigurability by displacing the CP lens with respect to the feeder. Now, to end, I'm going to show you here the validation by measurement of the CP lens. As you can see, the main beam can be tilted up to 30 degrees. Thank you very much.